Greetings everyone. Today we will talk about multi-agent decision making in our AI course. So because until now we have been talking about mostly about taking assumption that only a single agent is making the decisions, the sensing, and also the acting. So, but of course this is hugely simplifying, right? So of course most real life problems will involve multiple agents, right? So we can have some discussion on this, right? So we can have something. We can divide this problem a little bit in more different scenarios. For example, if we could have a single decision maker, right? Multiple actors, meaning making actions, but a single entity. So this modern classical example would be a single controller for a multi-drone show, for example, right? A single actually decision maker, meaning simple, agent would be this program, right? Which makes decisions, but multiple drones making different shapes, things like that. So this would be, of course, one decision maker. And here we do have this something called benevolent agent assumption, meaning that, of course, that these agents are basically do what they are told and act in the best interest of other agents, such as a human, manager, or possibly a AI, software program which makes the decisions as well, right? So this already becomes complicated because you need to do synchronization, right? You're making multiple agents have to act in unison, right? So they don't crash into each other, like as an example of drones, right? So there's this coordination introduce multiple levels of complexity, right? So this is called multi-effector planning, right? Multi-body planning, right? And also the question is, are we going to do a single? What kind of topology are we going to use? Is this going to be the single decision maker just transfers the information, decisions immediately to everybody? Or it's possible that there is something called decentralized planning, meaning the decisions are not immediately sent out from single source, but they are sort of require sort of like hopping, because there might be some communication constraints, right? So the plans, you need to have some communication between these units, even though they are not the main decision makers. Even if you still have the main source of authority, you still have to have this coordination within the smaller units. And then, of course, we could have multiple decision makers, right? Meaning, right, again, so now we get into the harder situation when, of course, you actually have multiple decision makers, but they are not necessarily acting towards the same goal. Maybe they even have the same goal, but they might have different preference, and they might have different opinions about reaching this goal plans. So again, may have a common goal, similar to all employees, right? If they all sign up to the company motto, right? They say, okay, yeah, we are going to go towards making the best, best computer, best tablet, best drone, whatever. They sign up to they drink the Kool-Aid of the company, right? So, or maybe, of course, right, might have different preference, maybe different subunit goals, right? So we get into the area of game theory, right, which is different from decision theory, distinct from decision theory, where you might have to think talk about different equilibriums, such as the famous Nash equilibrium, right, where what guides us towards, assuming everybody reaching their maximum amount of possible goals, basically, again, right? So you need to start considering this game theory, right, when creating agents, because otherwise, if you just sort of improvise completely without any accounting for any of the theory, it's highly unlikely that these multiple agents will work properly, right? So this, of course, example here is when you have multiple solitaire players. This is, everybody has their own game, non-cooperative, right? So this is, of course, simply if you have something like this, scenario like this, then you don't really have a big multi-agent problem. Basically, you can use, everybody gets their own single agent planning algorithm, and we can proceed, right? And so, but this is of course very rare, right? Because of course eventually you will have, most games, most scenarios, most real life scenarios will have some interaction, right? So in multi-agent planning, right, you will have to come up with plans, efficient planning algorithms, right? And of course a good, correct plan will be when everybody gets their goal, right? Again, it's possible not everybody gets their goal, but of course we try to reach the goal. That would be the goal, the actual, the highest possible standard. So again, we have to start modeling concurrency. Again, you already have some programming experience, and as you know, concurrency is apparent already in most modern CPUs, right? Because we have multiple cores, multiple threads. But here, of course, we have to somehow model because things are happening. Agents are acting, right? So if you want to model this, what's happening, right? You can do interleaved, right? In turn, right? So this is not probably a very good approach for larger assumption, because this means you say almost not turn-based, but yeah, it's in turn basically. Yeah, so one agent does A1 does something, A2 does something, A3 does something else, and so on. So true concurrency is basically that acknowledge that some actions can happen concurrently, and this will be more theoretical approach. And the third approach is to assume a global clock, again, not accounting for time travel and time, relative time, but basically synchronized. Basically have a global tick-based clock, of course, on every tick, so something happens, right? So those are the three classical ways of working with this, right? So now, so we come to this. What do we do? Well, we have to plan, right? So each agent independently creates its own plan, right? So, and again, we have knowledge, shared knowledge, right? We have goals. Even this is even assuming, right? So we could have multiple valid plans, right? Let's say you have multiple shortest path strategies for each agent, right? But again, you need to have a coordination, right? So, for example, right, like a swarm of cleaning robots, right? I'm sure you've seen the cleaning robots now or different fast food and different places, right? Even in offices, right? Well, these robots, they should coordinate, right? So that's actually a real-time consideration, right? So a simple one would be, of course, stick to your side of court, meaning if you are doing these vacuum robots, right, everybody gets their own side, and that's where they work, basically, and that's it, right? But again, that might not be optimal. Maybe one side gets more dirtier, right? Maybe then you would want to move more robots there, right? And I'm saying robots as agents in this case, right? So, and again, there could be some social issues, of course, conventions, right, for agents, right? So then you need, of course, establish some sort of communication, right? Some sort of protocol, right? Communication protocol, right? And of course, then you need to, of course, these agents have to recognize this plan that, and maybe there's a complete joint plan where you need to, which is the core goal, right? So again, if you define a concrete goal, right, without centralized control. Here we're talking about without control. There's not a single decision maker. Everybody is making their own decisions, but the goal is common, right? So again, so this picture here is from 1970s, I believe, from Sweden, or maybe in late 60s, right? So it's kind of famous picture. So what happened in this day? In this day, Sweden switched from left side driving to right side driving. Right side, like as we know, most of Europe. They use the English system, the British system of driving. So Sweden decided, hey, we are joining the Europe, right? And so there's of course a joke that this there was a little bit of coordination, right? Sweden being Sweden, of course, it was pretty peaceful. I don't think there were any fatalities, at least not directly attributed. But of course, you can imagine what kind of havoc breaking some sort of conventions, right? changes the whole structure of the of these all these are all agents, right? So now that we have discussed this cooperative situation where everybody has some goals, as such as not dying, we come to non-cooperative game theory, which means that there might be actually agents, of course, that might not have they have their own goals which might conflict, right? So usually this game theory starts with single move games, right? So this is something called, very, very, very primitive, you could say, decisions simultaneously, but you don't know the knowledge of the choices. So this is a famous prisoner's choice type of games, right? So you're making a choice, but you don't know what other agents do, right? So, and you have some sort of actions and payoff function, right? So you have players, but you can have two at least, right? And you have choices, right? And there's a payoff, right? So, so let's say you have to make a choice on prisoner's dilemma, right? Two people are interrogated, right? They were part of the same gang, and of course, if one is informs on others or other, right? They maybe go free or maybe serve less time. However, if they both confess, then they go for a long time. There could be different payoffs, right? You probably heard of prisoner's dilemma, and you also might have heard of Nash equilibrium, where there is actually players cannot change their strategy if everybody else's strategies remain unchanged, right? So every game, as far as classical game theory, has at least one Nash equilibrium, right? So possibly multiple, right? So also there could be some. You have to introduce a concept of social welfare, right? So what does it mean here? That's different perspective. So maybe there is sort of like outside view, somebody, I wouldn't say a higher being, but somebody outside of this game, right, is saying, okay, so they want to choose the best outcome for the society as a whole, right? So then this is a way of inspecting this, if these decision agents are actually Pareto optimal, means that nobody suffers basically in the same way, right? So we try to improve the whole society outside of these small agents, basically, right? So that also introduces another aspect, right? So meaning egalitarian social welfare, right? So maybe we want to see again. So not only somebody getting extremely rich, but we also want to keep this egalitarian society. There is something called Gini coefficient, meaning which says how equal as a society we are, right? So again, not only somebody being extremely well off, one agent winning everything, right? We also want to keep the sort of overall well-being of these agents, right? At a good level, meaning so there's no so we don't want to we want to keep distribution more equal, right? So of course this is not always this is not a solvable problem, right? Different countries approach it differently, and again within these agentic systems, of course, there are different ways of dealing. Maybe it's okay if somebody takes everything, but maybe it's completely not okay, right? Maybe one agent shouldn't win everything, right? So okay, so let's look at some games. We'll look at some games, maybe some examples, maybe later on. But so how do we find this equilibria, right, in pure strategies, right? You might want to just keep looking at all the search of different strategies and basically, enumerate, brute force search, right? You have a simple game. This is very simple, right? But there is a strategy by who else but John von Neumann, of course, our friend who does pretty much everything, right? Who did everything in 20th century, and he was a big pioneer of game theory. So Max-Min method is, ensures that player cannot do worse by revealing their strategy. Meaning, so if player, the way it works, if player says what they are doing, that's still, meaning they being completely honest with everybody else in the game, they cannot do what they strategy still stays the same. So being honest is the best policy, and it helps to solve this equilibria. Now, of course, we have to think about repeated games, because there's a big difference. If you have, so let's take a 100-round prisoner's dilemma, right? So you have 100 games, right? So last game is single shot, right? So if you know 100 games, right? This means we will choose testify against each other, right? In every round, leading to suboptimal outcome for boss. Maybe I should show you what prisoner's game is. Actually, prisoner's dilemma, classical way, right? If you have not read it yet, I'm sure you have, right? Because there are different payoffs, right? So usually, right? So this is a prisoner's dilemma, one of the ways, right? So two prisoners, right? So if they are both silent, they serve 1 year, right? If they both testify, meaning, full information of the gang, they serve 2 years. Of course, these numbers could vary, maybe 20 years, right? Maybe it's only, if they're all silent, maybe they only take 2 months, right? Of course, that could change sometimes. So, but the main point is that if they testify, the other agent suffers and they gain, of course, right? So this is the point. But here they both testify, right? So, so the thing is, now, where the issue is, so no matter what the other decides, everybody, each prisoner gets higher reward by betraying the other, right? So how do you come up with this idea? So B will either cooperate or defect, right? So you have only two choices. That's why it's a super simple game, right? So if B cooperates, A should defect, right? Because going free is better than 1 year. If B defects, A should also defect, because 2 years is better than 3. So meaning, what this means is, no matter, so if you analyze, if you are in prison and you're having this choice, hopefully not, right? In each case, no matter what the other guy does, you are better served by testifying, right? So you don't care. So that means if both are smart, well, not all prisoners are smart, but in either case, the equilibrium is here, right? So, meaning two rational agents would both be testifying. And of course, the irony of this is that, of course, so they would serve 2 years, right? If they could somehow decide, of course, they would serve 1 year. So that's why it's really fun, right? So defection always results in better payoffs than cooperation. So it's strictly dominant in this particular example. So mutual defection is the only strong Nash equilibrium in this game, right? So hopefully you can see this, why this arises, right? So again, if somebody is very, have some ideals, they don't cooperate, right? It doesn't matter for the other agent, other guy, basically. So so that's so here's the talk. We're talking about 100-round games. Rational player will still testify because, of course, it's only 100 games. However, right, so this is very interesting. So infinite games, you don't know how long they're going to go, right? So what happens then? Well, it's interesting. In real life, right, so there's a couple different strategies. And one of the most interesting strategies is called tit for tat, meaning you start out by, if somebody starts defecting, right, informing, you also start informing, because okay, assuming you can do this every year, right? You go, or every couple of years, or this game repeats and repeats and repeats, right? So there are a couple of strategies. So hawk, right, always be aggressive, though always be, the different strategies for multiple games, right? But tit for tat has actually been proven, I think, the most effective in real life, right? So. Right, so tit for tat is mimic the opponent's last move, right? Grim is permanent retaliation if somebody defects, meaning if you break the equilibrium, right, then you become really retaliate and you be bad, basically, right? So this, of course, makes there's no strategies change, right? So possible, right? And you see, okay, if we start, somebody maybe is like, let's go back to our. If you do this multiple times, somebody stays silent for a couple of times, and if tit for tat, both implement tit for tat, right? Then of course, eventually they might go to here, right, and start gaining instead of this, right? So it's very interesting, actually. So I highly recommend, maybe if you're interested in this, doing some more research. Maybe we'll do some more examples of code examples, playing these games, right? So here's actually a visualization of this, right? So Hawk, right? Always testify, right? Refuse, testify. Though is always refuse. So meaning state, these are so-called finite state machines. Finite state machines. We talked about this before in the algorithms class, right? So in this case, there's only one state for Hawk and Doe. Grim refuses, right? And as soon as somebody, so this outside, these are the opponent's moves, right? So if the opponent testifies, they also start testifying, and that's it. So tit for tat is the one which is, or tat for tit, right? So you start by refusing, meaning you don't inform, and if they testify, you start testifying, right? Testify. If they refuse at the moment, you go back to refuse. So tit for tat. There's other one. That for tit, rarer one, right? So you start by testifying. If they testify, you refuse, right? Kind of very reverse psychology. I have not read much on this strategy, but might be interesting to see where this would actually make sense. Maybe there might be some scenarios where this makes sense, right? So these are basically names for finite state machine strategies, right? So hopefully that makes sense, right? So all of these different strategies, maybe you can, is there anything else possible? Of course, as more states are introduced and more opponents moves are possible, right? More agents. I shouldn't say maybe opponent, because again, sometimes they might have similar goals. Now, sequential games, right? So, like regular games, right? So we have turns, right? So not the same game repeated multiple times, but multiple turns, right? So of course, state transitions, right? Stochastic information. So again, just like chess, for example, right? Sometimes we assume it's perfect. If we assume perfect information, it's just like chess, right? So there's a strategy, of course. Maybe you have a game tree where it leads to, assuming you can build a full game tree, right? So. But of course, also remember we talked about also things like Kriegspiel, right? Where we don't have full information, right? So these are not solvable usual standard methods, right? So what you usually do, of course, you can do things like in poker, right? You can do some sort of simulations, right? Meaning Monte Carlo tree search. What does it mean is we sample from the variation tree, right? Use the quite a bit these days. When you have a huge game tree, you can't have brute force search, right? So you maybe sample and then maybe use some approach there to simplify search. Now, right, another thing, of course, is that maybe the payoff is not known, is not certain, right? So there could be, I can remember our ice cream example with the durian, the not tasty ice cream, which might be good, might not be good, right? So we might have a situation where maybe if the robot is not sure, it could just turn off, of course, right? So again, we have assistance game. We have two-person game model. You have a human, H, right, and robot Robbie, right? So Harriet knows. She knows what she wants, right? Robbie just only has a probability, right? So, and of course, this is a beneficial AI example. Robbie wants to help Harriet, right? So, eventually, right, so, he can understand what Harriet wants, right? So, on Robbie updates its own. Again, it's an agent, right? Non-human agent, in this case, updates its own preferences, right? And probabilities of what can do. So there could be a simple game this is a so-called paperclip game here, right? So let me see. Yeah. So Harriet wants some paperclips, right? Basically, you have paperclips and staples, right? So Harriet, right? She can indicate how much she wants the paperclips, right? And then Robbie acts on this and maybe, increase the number of staples, basically, right? So sort of Robbie follows Harriet's signaling, basically, right? So now, cooperation game theory, right? So remember we have a cooperative games. What do? They capture decision-making scenarios where agents can form binding agreements with each another. So, of course, these cooperations can be temporary or permanent. Temporary meaning just for a moment. If you think of countries as being agents, right? They can make temporary agreements and maybe longer-term agreements, right? So, cooperative game theory, right? And so, as you all probably seen, games like Survivor, or pretty much any of these games, usually it doesn't mean the strongest player might not necessarily win in some games, like in society. Cooperation, you have these sub-coalitions, and there might be a grand coalition, and so on, right? So, a subset of players, then coalition, right? So, everybody is grand coalition, right? So, of course, in this particular version, right, this is a simplified version, you only have single coalition, right? But of course, you could make it more multiple coalitions also are possible, right? So, that's a sort of standardized way. So, what happens, what kind of strategy we have here, right? So, again, of course, the goal is to, payoff, right? Whether it could be survivor, in a game of survival, right? Eventually you want to be the winner or the only one last standing, right? So again, I'm sure you've seen Hunger Games. That's exactly what happens, right? In Hunger Games, right? We have coalitions, right? And again, maybe strongest take the other stronger ones, right? But maybe we can also group up, right? So, and of course, it's possible that it's not very beneficial to break away from a coalition, right? Again, so somebody can do something alone, right? So there is something called Shapley value, right? Which is basically which has some fairness axioms, right? So which is basically how to divide this payoff, right? So this Shapley was a Nobel laureate, right, in 1950s, I believe, and he proves this fairness standard, right? So it rewards players based on their contributions to the collective success instead of just something arbitrary, right? So it's a way of formalizing. Again, what I'm all talking about is maybe not strictly formally at this moment. The main thing is at this stage in the game, so to say, in your AI journey, so to say, is to think about these ideas in general. Meaning you have to be aware of them, right? As on a need to have basis, you might need to actually calculate it, but you need to be aware when you're building a multi-agent system, of course, right? So, so how will you computate this actually, right? That theoretically we can actually provide this. So there exists something, there is a equitable solution basically, right? So there's ways of doing it. There's something called marginal contribution nets. We call these MC nets, meaning that improvement, right? Yeah, here we have marginal contribution nets, right? So a structural concept, right? So game's characteristics function through a series of rules, right? And you can have these rules, and they provide, given a rule set, you have the values for each coalition. So meaning means no coalition, grand coalition, right? Maybe some sub-coalitions, and you can calculate these changes in the Shapley value, basically, right? So, and again, maximizing social welfare, right? So, again, maybe you want to maximize the overall productivity of the whole game world or our world, right? Or not only just individual strategic considerations. So yeah, and sometimes of course you have to make so-called collective decisions. So what do I mean by that? 1 second here. And I am a little bit. So here we are. So we want to design a right game for a collection of agents to engage in, right? So we want to have a language. We have an agent center, collects reports, an outcome that everybody will know that center will use to have payoffs, right? So we could do, again, have a we will have a central authority, like the main agent, right? We'll have an outcome rule, right? And then we have to allocate the tasks, right? So you come up with so-called contract net protocol, which provides this sort of way of sharing these tasks. The agent, we need something to do, right? So you need help. So you are this little cleaning robot, right? You need help, right? Your agent needs help. You broadcast there's need something, others on the network, and there are details for the bidders to help with this task, right? There you have to submit bids, right? Meaning bids, what can you do? What the agent has, what this individual agent has is able to do, right? And there is a manager, sort of say, which evaluates and then assigns the tasks. So this is sort of centralized planning in this moment, right? And there actually a task execution. So this is pretty well known actually, right? Makes sense actually, right? And you award the contractors, right? Who wants to do. So these are all sort of say benevolent agents in this case. We're back to benevolent agent world, right? So, right. So how about next we come to allocating something scarce with auctions, right? So again, we could have a lottery. We have something, who gets a new kidney, right? No, who gets a new heart? Well, maybe who gets a new car, right? We could do, of course, a lottery, right? But auctions generally will be more effectively, well, auctions, meaning there are agents competing for this, right? So auction mechanism, right? Signals, it's a better way of signaling than just randomly assigning, right? So there are different ways of auctions. You probably know the classical is so-called ascending bid auction, right? Start minimum bid, you have some given time, right? And no further bids are taken. But there are other ones, right? So of course there is a problem with collusion, right? So if you have only a couple bidders, you can keep the bids low, right? And you have, let's say you have multiple cell phone spectrum, right? You have multiple frequencies, right? So collusion means what? Two bidders, one bidder maybe wins one bidder wins another one a little bit more, but they keep the bids low, right? And of course, who loses? The German government, the German people lose, of course, in this case, right? So again, so maybe changing reserve price could have been maybe a sealed bid auction. This means you submit a bid, right? But you don't know what other guys did, right? And it's not open, and it's only one time bid maybe, right? Maybe invite more bidders. There's many ways of encouraging this. There's many different type of auctions. Different auction mechanisms that we can adopt to simplify right participation and encourage truthful bidding. So, by the way, it's very interesting. Vicray auction, very interesting auction. It's used by Google for their ad allocations. So what does it mean? This is very interesting. We all bid, but the winner pays the second highest bid, right? That's interesting, right? Interesting approach. What's the grand idea is that you are more motivated to provide your highest, actually, what you want to pay, right? So this leads to higher paying because you yourself are not going to pay the maximum price. You're going to pay the price of second guy, basically, right? So this actually happens. It's very good for those who are holding these auctions. Turns out people tend to bid more then, right? Because you're not going to be overpaying in your own mind, right? So it's interesting, actually, right? So the different ways. So you probably heard of strategy of commons. What's strategy of commons? Meaning, classical example would be if, well, like right now we're dealing with global warming, unfortunately, sadly, right? No country, like especially some of the bigger countries, I'm not going to name any names, but you probably know of them, all of them, right? Major industrial players, it's not much in their interests to reduce pollution, right? Because, well, Earth, 50 years, right? right? They don't have to worry about now. They get payoff right now. And also, it's like, well, we have to continue, but okay. So, dominant strategy is pollution, unfortunately, but everybody suffers. So strategy of commons, meaning, so again, we can all dump our dirt in a single river, so it's useful, so because everybody pays for the river, but not everybody individually, right? So this is a common resource, even checked, right? Everybody exploits it and everybody loses, right? So this is extremely problematic, right? So how do you solve this? Well, we know, of course, carbon tax is one example. For example, there are different ways of how to, we need to introduce this global utility. Otherwise, nothing will work, right? So this is extremely, basically, well, challenging problem to solve, right? So we come to some other things, right? We going towards the end. So voting, right? How we make choices. Maybe agents get to make choice, right? Aggregation of individual preference. That might be something we might want to introduce in your multiple agent swarm, right? Maybe, right? So there could be some interesting challenges, right? There's no candidate is preferred by majority over every other candidate. So, so any outcome can be contested by the majority preferring a different outcome. That's very interesting, actually, by the way. Concordance paradox, I'll mention this if you want. This is explore this afterwards, right? This one here. Yeah. So it's like A to B, B to C, and C to A, basically, right? So you have a tie. So his example, right? 3 candidates on voter A prefers A to B, right? A, B, C, B, C, A, C, A, B. So basically, there's no winner by, when you compare two winners, there's always going to be, there's no equilibrium, basically, right? So we can find another alternative that will be preferred by most voters. So we can always find some combination that will be preferred more. Very interesting paradox, by the way, right? So, right. So if all voters prefer one outcome over another, the social preference should reflect this, right? So a couple interesting things here, right, about voting. So yeah, yes. So, and of course we have to deal with, well, manipulation, right? So meaning that there might be situations where we, well, oftentimes when we don't provide completely truthful reporting, right? So again, as you've probably seen of these different various election type of systems where voters say one thing, but they actually do something completely different, right? So the signaling is broken in a way, right? But again, it is because individually the agents are making rational choices, right? Sometimes irrational, but right. So, for example, plurality systems. Voters might choose their second preference if their first choice seems unlikely to win, right? So, if the first, they have somebody they really like as a politician, right? But they are not popular among others. You know, their friends, your friends will not vote, but you have somebody who is still within your interest sphere, right? But maybe not as good as you think, but you know they have a more realistic chance. So this means, of course, that middle of the road candidates usually tend to do better. And again, I'm sure you've seen this play again and again in voting in real life elections. It happens all the time, right? Sometimes you see they have these coalitions that people who maybe some strange, so politics make for strange bedfellows, right? When different people decide, different coalitions, people, agents decide to vote, maybe for the candidate which is maybe not their main interest, but is better than the is still better than the, well, alternative, of course, right? So and then we have to also bargaining, right? Meaning, again, depending on the country where you go, right, it might be part of everyday life, right? So somebody will be angry if you're not bargaining every day, right? So you need to arrange, maybe somebody has one proposal, you have to introduce this bargaining process, you know, back and forth, right? Different agents might have different ways of dealing with this bargaining. Do you do a single scenario, right? You propose and you reject, right? So there's A1 has a full power. There could be multiple scenarios, 2-round scenario, A2 can reject, right? And then propose again, right? And then it could be other things. So impatient agents, right? Could be negotiation, task-oriented domains, right? So also there might be a protocol where you need to negotiate who is going to do what. So you will have multiple rounds and we propose who's going to do what, and there is a well assigned protocol how we deal with this. So again, another thing to consider, right? So there is something called Zuten strategy, right? How we are, which guides agents how we're going to need to behave during negotiations, basically, right? And again, just need to be aware of this, right? So let's summarize this whole, right? So we have multi-agent planning. We might need to coordinate. Possibly we need to compete, right? So this will need, what this requires, joint plans and coordination, right? So you need to be aware of game theory. There are well-defined frameworks within game theory, right? Deal with this, right? There are different solutions. And again, no perfect ones, right? Sometimes these games become really grim, right? So hopefully you will have to work on some nice games, right? So there's some specialized techniques for multi-agent decision. So lastly, there are some key papers, right? So key papers, Minsky's Sophisticated Mind is good. Formalization, so early proposals for game theory, formal proposals, but of course this is Oscar Morgenstern and John von Neumann, Theory of Games and Economic Behavior, 1944, right? And of course there's John Nash, you've probably seen the movie about him, Beautiful Mind, right? He came up with this equilibrium concept. Again, doesn't seem so hard, right? So, different games, and some more readings if you want to read on this. But again, so now, hopefully from this chapter you see how, if you're dealing with multi-agent systems, what you have to incorporate. And this will lead us to our next lecture when we're actually going to start thinking about machine learning. So thank you, and we will continue in the next lecture.